So let's unpack this. They tell us a spherical balloon is being filled with air at a constant rate of 2 centimeters cubed per second. So let me write the 2 over here so it's easier to see. And then I want you to look at this guy right here. And I claim that by looking at that number, that highlighted number, we can really tell what kind of a rate of change this is. So when you guys look at this 2 centimeters cubed per second, what is it that's changing? In other words, I'm looking for you to say, oh, this is d something, and I want to know what the two variables are. Does anybody have any feeling as to what those two variables are? What the top variable is and what the bottom variable is? Some person in the chat box privately says area. And can anyone say why the answer is not area? Why is it not area? Does anybody know? The units. You all love it messaging me privately. That's cool. So if you look at this, this is centimeters cubed. Centimeters is length. Centimeters squared is area. Centimeters cubed is volume. Does that make sense? So this is going to be, the top part should be the rate of change of the volume. In fact, I don't know why I do it in red. I can do it in blue. So this guy is going to be, dv dt is equal to 2 centimeters cubed per second. I have a question for you. How do you know that this is positive 2 instead of negative 2? Any thoughts? Why is it positive 2 and not negative 2? Maybe it's obvious, but just wanted to check. That's right. It's being filled with air. So if it's being filled with air, that means the volume is increasing. Increasing volume means that the derivative is positive. If it was going to be negative, it would say air is leaking from a balloon. When they say leaking from a balloon, then the derivative would be negative. Does that make sense? So right away, we identify that we have a very important piece of information here. Okay. The next thing I want to unpack with you is if we look at this next piece right here, let's change up the color. If I say, how fast? When they ask me how fast, they're asking me for a rate of change, right? How much would be sort of the amount of volume? How fast is the rate of change of something, right? Like velocity is how fast something is, right? So how fast is the radius increasing when the radius is 3 centimeters, okay? So what this question is asking us is how fast is the radius increasing? So how do I describe that little phrase there? I think they're asking me dr dt. Does that make sense? So they're not just asking me dr dt in general, they're asking me at a specific moment in time. They're asking me how fast is that radius increasing when the radius is 3. So the way that I express that is I put a little vertical bar and I said r equal to 3 centimeters. And this is what we're looking for. Okay. So I've read the question. There's one piece of information that I haven't used yet. I haven't used the fact that they gave me a sphere. So this is a spherical balloon. That's going to be important for us. in a moment. So before I continue with this problem, I want to go back to what I had started talking about over here. So we know that dv dt is going to be related in some way to dr dt. I'm curious if anybody knows what would go inside over here. And if you do have some feeling, why don't you type your answer in the chat box? No one has any feeling. See, what happens is you find df dx, you have df with respect to some intermediate variable times dg dx, right? So I have a couple of guesses now in the chat box, and I think those guesses are correct. What we would want to write here is we want to write dv dr. So what's happening is we are relating these two rates, right? So dv dt, first you do dv dr, then you do dr dt, and it's almost like the drs cancel out. So these related rates problems, the way we relate the rates is by using the chain rule, like so. You could also think of it as implicit differentiation if you want. It's the same thing. Okay. And the way that these word problems work is you see there's three rates here. Usually you know or are given or can calculate two of the rates and you're looking for the third one. That's usually how these problems work. And the key to being able to do these problems is to really set up a good model. So a lot of time the model is involved in setting up this part right here. And now this question, this question that we're looking at, once they tell me it's a spherical balloon, they're giving me a model. So does anybody happen to know what the volume of a sphere is with respect to the radius? Anybody know? I can tell you, but I'm curious if you know. Anyone want to take a stab at the volume of a sphere? Nope. It's 4/3 pi r cubed. Okay. So the model that I'm talking about is really given in this problem, the spherical balloon problem right here. But in the more complicated problems beyond example 1, we're going to have to construct the model, and that's its own skill. Okay. Cool. So so now that I have the volume, I can apply the chain rule to relate the rates. So what we did right here was this related the variables. So let me organize this a little bit better. Let me move stuff around. This example, I don't think takes too much space. So let me give you some commentary on what we're doing here. Okay, I'll put the commentary in red. So this is the given information, right? This is what we are looking for. And this is relating the variables. I'm trying to sort of describe the process I use to reason this out. After you've related the variables, the next thing we want to do is want to relate the rates. And the way that we relate the rates is we take the derivative with respect to time. So here's where I use the fact that dv dt is equal to dv dr times dr dt. So in this case, dv dr is going to be 4 pi r squared dr dt like this. Is there any questions about what I've written so far? If you have any questions at all, you should ask. Because I kind of want to master the basic case first, and then And then the harder problems would be more about modeling the situation. Okay. All right, cool. So, as I had said earlier, they usually give you 2 pieces of information and you're looking for the third one. So what I like to do is I like to solve for the thing I'm looking for first. That's why it's important to know what you are looking for here. So let's isolate the dr dt. So we're going to get dr dt is going to be equal to dv dt divided by 4 pi r squared. Right? And I really wanted this evaluated at r equal to 3. So let me fill in the pieces. They tell me what dv dt is. Terry, I just saw you put r cubed. Why did you put r cubed there? You have a question about the r cubed? Because I took a derivative. That's why it's 4 pi r squared. Does that make sense? Took a derivative. Yeah, dv dr, right? It's not just v, it's dv dr. You got to use the chain rule. You got to take the derivative. Okay. So dv dt is equal to 2. And the denominator is going to be 4 pi times 3 squared, like so. So you simplify this down, you're going to get 1 over 18 pi centimeters per second. And that's going to be our answer. Is there any questions about this? So let's break down our process now. Our process was, first we assign variables to the quantities that are changing. Oh, it's unreadable. Okay. The next thing we do is we state the information given and the rate to be determined. So I didn't exactly specify that V was equal to, maybe I should do that. Maybe I should have said V is equal to volume, R is equal to the radius, T is equal to time. I mean, probably I teach math so much, I just automatically assume everyone uses those letters, but you don't have to. Just use it automatically. Okay. So, but we definitely did the next 2 steps, which is, express the given information and write down what you're looking for. It's pretty important. The next thing we want to do is want to find an equation relating the rates. And then using the chain rule, we're going to differentiate both sides of the equation with respect to the independent variable. And for us, it's almost always time t in this section. Okay. Finally, you want to substitute in the known quantities and solve for the unknown rate. This is basically how all of our problems are going to work.